Okay, so this is a diverging lens diagram. Um, we're going to kind of draw our lines there and on this one, and then we'll do calculations kind of like we did on the converging. Okay, so first off, let's start with the first line we'll draw. Very similar to the converging lens, you go along the principal axis. But then what you do is you line up with the negative focal to figure out how much the lens is going to diverge. Remember, diverging means it spreads out. So we line up with this negative axis right there, and really what you do is you take and make this a dashed line behind, or I guess in front of, if you consider this over here in front of the lens. But on the negative part of this axis, you make this a dashed line, okay? All right. So that's kind of the way our diagram looks. It's dividing out the line for the first line, okay? So there is line number one. Okay, line number two, again, we kind of do a similar thing to what we did before. We're going to line up with this focal length right here. Okay, and I'm going to switch colors. Let's go with that darker blue. Okay. No, let's go with green. We'll go green. Okay. All right. So you line up with this right here with that focal length. Okay. But it doesn't actually take and go that direction. Okay. What happens is when it hits the center point, it's going to flatten out along this axis, just like that. Okay? Where these converge, and right now that's not actually where it's going to be. Okay? What we have to do is you have to take and say you trace this line backwards this way. Okay? And again, you make another dashed line right there. Okay, now it's where the dashes are going to hit that the object actually appears. Okay, so I'm going to go ahead and do a similar color there. And so the object is going to appear about right there. Okay. Let's make it yellow. Alright, so it's going to be appearing right there. Alright, and you notice right now it's upright. It is in front of the lens where the lights really aren't. I mean, the light really is over here on this side, but it's appearing like it's over here. Okay, so this type of lens, by the way, is used for people who are nearsighted. Okay, or the term is myopia or myopic. Okay, because it spreads the light out. I'll show you some others as to why we use lenses the way we do like that. Okay, all right, the third ray, and we can go ahead and just draw that in so you can see it. But the third lens is going to go straight through just like this. And you notice it converges as well. Okay? Alright, so it's upright, it's reduced, it's virtual. Those are the things we know about this. I'm going to pause, and then we'll start again with a few other things with calculations. Okay? Okay, so we're going to do the diverging lens calculations. We use the same equation that we have been. 1 over P plus 1 over Q equals 1 over F. We're going to say that our F value is equal to 1 again, except we're using the F on this side for all of this, which means it's negative. Okay, and the p-value is 2.5, okay, which is positive. Okay, we have positive p but negative f on the same side. Okay, by the way, this would be negative q and this would be positive q. So let's look and see what happens. We should end up with a negative value for the image distance if our diagram's right and if our math confirms it. So let's go ahead and work it out. 1 over 2.5 plus 1 over q equals 1 over negative 1. So I'm just going to go ahead and write that, negative 1. Okay? So that's 1 over 2.5 is 0.4. So I'm going to go ahead and move it over. So 1 over q equals negative 1 minus 0.4. Okay? So that's 1 over q equals a negative 1.4. Okay, so if we do the math and we swap the q and negative 1.4, we get 1 divided by negative 1.4. And so q works out to be about 0.714, except it's negative, okay, a negative 0.714. So that means this should end up about 3/4 of the way from the lens to the focal point, and that looks pretty good. 7/10, 3/4, that looks pretty close, okay? So we look pretty accurate there, okay? All right, and because it's negative, that means it's going to be on this side, right? So negative q for the diverging lens, okay? All right, now the next thing we can do is we can do magnification. So let's look at that. Magnification is going to be negative q over p, just like before. Okay, so we do a negative times a negative 0.714 divided by 2.5, right? So that's 0.714 divided by 2.5. And we get about 0.2856. So that means that is the percentage of what it started out. So we say this, maybe we say this started as an inch. This would be 0.2856 inches. Okay. Now you notice it's positive. So it's positive, which means it is upright, which it is. Okay. So upright. Positive value, upright image, that works really well. It's smaller than 1, so it's reduced or diminished. Math confirms the diagram. Okay, and the last thing we have is it real or virtual? Well, we expect the light to be over here, but it's like the image is coming from over here. So that means this is actually a virtual image, because it's like it brought it up. That's why this is what's used for nearsighted. Nearsighted people have to bring something close to their face. This type of lens is like it brings the object up close to the face or close to the lens, and it spreads it out. Okay, I'm going to do one more video to show you guys why you use diverging or converging lenses with certain eye issues. So there you go. Thanks. We'll probably do that one, and then we'll do one on color. So thanks.